All right, well, good evening, everyone. Welcome to the August meeting of the Ottawa Centre, or the RASC. My name is Mike Mogan. I'm glad you could join us tonight. First of all, I wanted to just ask everyone, the video we just watched, the documentary narrated by Jodie Foster of the VLA, do you like it? I mean, maybe if you like it, give me a hand up.
I loved it. Yes.
Okay, so that's encouraging. We'll do more of that, I think. We've got a number of video suggestions that have been raised. Chris has been suggesting them. Maybe you have some suggestions on some short videos that we could play before the meeting here. So let Chris and myself know, and we'd like to do more of it. Officially, the meeting will start at 8 o'clock. I know there was a couple of people who were asking me, does the meeting start at 7:30 or does it start at 8? It starts at 8, but we'd like to do this just to sort of get everyone settled and, I don't know, maybe get everyone in the mood. Okay, so this, I like this too. I watched this video the other night, and I watched it beginning to end. All right, we've got a fine evening. Let's next slide, please. All right, so usual stuff. Gary will talk about Ottawa skies. This is what we can expect to see in the sky this month. Al has got a topic of interest, and I am. Does anyone have a guess what he could be talking about? Yeah, somebody already got it in the back. Yeah, it's that. You'll see, but Al's done an amazing job, as he always does. Okay. So Peter Heyman is going to talk. I mentioned in the agenda that I posted on the web for this meeting that Peter he's off to do his master's in theoretical physics, and he's giving us a presentation before he goes off to McMaster here. I have to tell you a story about Peter, which is pretty funny here. I mean, I remember when Peter was just starting his physics at Carleton. He said nonchalantly, as he says just about everything nonchalantly, he said, I think I'm going to go through and all the way to my PhD. Okay, now this is, people who are starting university tend to be a little bit, they find the experience a bit daunting, but Peter, his hands in his pockets, saying, this is what I'm going to do, and he's on the path, he's doing it. So somehow I don't remember it that easy back in my days. So then we're going to have a break and pick up the tickets for the raffle tickets for the door prize. Okay, so for those of you who are new tonight, we raffle off a bunch of books and various astronomy-related things up front here. So pick up your ticket. You don't have to be a member to possibly win one of the prizes. Short break followed by another presenter from Bianca Daus, who is going to be talking about impact craters on Mars and the meaning of the impacts on Mars. So a subject of interest to, I know, a number of members tonight. And then we have a full suite of observations. So next slide, please. Still more members. This is really great. So in yellow there, you see Ingrid, Heather, Jason, Joel, Louise, and Jacqueline. Is anyone here tonight? If you are, please say, I am here tonight. I see somebody's hand in the back, but I don't hear the I'm here tonight. But welcome. It's nice to have you here. And maybe if there's somebody else I can't see, it's dark in the audience. It's nice to have you as a member. We've got a terrific suite of benefits for members, and I'll talk a little bit about that later on. And we have a membership card. I don't mention this enough. Art Fraser, who mans the coffee table and the refreshments table at break and after the meeting, he has the membership cards. Okay, next slide. So members in the news. Okay, so this is interesting here. Chris spotted this in Sky and Telescope recently in the August issue of the Sky and Telescope. It talks about some of the Canada's dark sky preserves and so forth. And if you read it here, it's you can see the print, but it says something here. It's, over the past 15 years, Canada has quietly set aside 80,000 square kilometers. It's almost hard to believe, for dark sky preserves. And if you dive into this, there's one person who's really, they talk about how the RASC really has to approve these dark sky preserve designations. And if you really dig into it, and if you go onto the rasc.ca website, you'll see the name of Rob Dick, okay, who's the chair of the Light Pollution Abatement Committee. He's active in all things dark sky. So, Rob, I didn't see you here tonight. Are you here? Yeah. So, Rob, thanks for all you've done. Rob's hiding in the dark in the back. All right, next. So this is another thing that's really interesting that just showed up in the journal. Do you remember Frank Roy? Frank, he's a Ottawa Centre member, in fact. He came about a year and a half ago, Chris? About a year and a half ago to our meetings and talked about a Madawaska Highlands Observatory Corporation. And what it was setting up an observatory, a planetarium, observing area, a place for school outreach and so forth. And you remember he was talking about funding and he was looking for investors and so forth. He just secured $3 million of investment. So, wow. Okay, so this is a terrific start. Frank, if you're watching this, well done. That's awesome. Okay. Okay, next up is Gary Boyle, but I want to say something before we get started. Gary is our new, as you know, he's our president, of course, but he's also our new high energy outreach coordinator. So, Gary, welcome. Thanks very much.
Thank you, Mike. Well, I figured I'd double my salary. And yeah, just to let you know, I was in the news 2 hours ago. I was interviewed by Matt Scooby today on CTV about the supermoon, and they played tonight at 6 o'clock. So awesome. I was on with Scooby Doo. First slide, great. Well, the Summer Triangle. Summer Triangle is. First of all, how many first-time visitors here tonight? Excellent, great. Thanks for coming. Yes, round of applause, round of applause. Well, the Summer Triangle really is the collection of 3 of the brightest stars in a certain area. Here we have Deneb, Vega, and Altair. And pretty well, they're the brightest stars of Altair, the harp. Aquila. I was testing you. Vega, and Deneb. So they're all pretty bright. They're easily naked eye. They're about 3rd or 4th magnitude. Next slide, please. So stars are like the sun. They're huge balls of gas, but they all orbit or have different principles. Because you can see the sun is a nice round ball over here, and it's only 2 light minutes from Earth, and it's about 2 kilometers per second as it spins. We can see that Vega is only 25 light years away, but it's spinning extremely fast, and it's about twice the size of the sun, 2.8 times the size of our sun, but 274 kilometers per second. And then we have Altair, called the Sweet 16 star. Anyone about 16 years old here?
I am.
Times what? But if you're around 16, or anybody watching on the internet, if you're 16 now, the light left around your birthday. And that's what a light year is, just the light travels in 1 year. And you can see how it does move extremely fast too. It is smaller than Vega, but still bigger than the sun. It orbits once every 9 hours. So actually the equator is 20% larger than what the pole measurement is. It looks like an egg, so it's really, really spinning fast. Next we have Deneb. And this is quite incredible how stars can really be. If we take 109 Earths, which you can fit across the belly of the sun, you would have to take 110 suns to go across Deneb. Or doing the math, it's almost 12,000 Earths across Deneb. And some stars are even bigger. That's what's just mind-boggling about astronomy. Okay, next slide, please. So here we have, next to Deneb over here, we have the North American Nebula. It's an emission nebula, which means stars are being produced over a very long period of time. So we have the North American, which takes on the very, very distinct outline of our continent, and this looks like a pelican, the Pelican Nebula. It's actually one of the same field, or shell of gas, just that we have some dark matter here that's between us and the actual gas, so it's bringing on this silhouette. It's pretty hard to see naked eye, but photography really brings out the colors. And it's only 2,200 light years away. Next slide, please. Our next object will be over here. Right next to Vega is a double star, and it's Epsilon Lyra. And looking at a close-up of that one is a great little sketch. Now, in binoculars, you'll easily see 2 stars. But in a telescope, which is a great test for your telescope, if you can split these guys, they're again double again. So we call it the double-double or the Tim Horton star. And the gap is very small. It's only 2.3 arc minutes and 2.4 arc minutes. So it's very, very small separation. So depending on your night, but mostly how well the mirrors of your telescope are collimated. Next slide, please. Next we have over here, if we take the HARP, sorry, the HARP over here, it's pretty well a rectangle of stars, 2 up here and 2 down here. Pretty well right in the middle is another great object, M57. And the M, which is in front of a lot of objects, stands for Charles Messier, who was a comet hunter back in the 19th century, 18th century. And he saw these faint fuzzies when he was looking for comets, decided they weren't comets, put them on a star chart. And now it's a great way for amateur astronomers to begin looking at the sky, looking at these semi-bright objects, which many can even see with binoculars. So next slide, please. So here's the Ring Nebula, M57. And really it's just pretty well a dead star. It's a planetary nebula, has nothing to do with a planet, but does have size to it. And what will happen to the sun in another 5 billion years? What happens is the star does not blow up, but it becomes a red giant. The outer shells begin to fluff off in space because not enough strength to hold it together anymore, and just makes this beautiful ring in space. Sometimes they're rings, sometimes they make these beautiful designs. So with that, then we also have next to it is IC 1296, only 220 million light years away, or 100,000 times further than the ring. The ring is in our own galaxy. And if you really want to go further, is PGC 2813669. They estimate it's about 30th magnitude. Couldn't really get any details on it. So we'll just say it's a galaxy far, far away. It's extremely far away. So if you ever take imagery, deep images, which you can tell with the Ring Nebula, again, this outer halo is a pretty deep image. Next slide, please. Well, one of the, or pretty well the best comet in the skies now, in the morning skies, evening morning skies, is Comet Jacques. Jacques is moving out of Auriga now and moving pretty well booting through the sky until it meets up to Cephas. So if you want to check out a comet, although with the full moon coming up these nights, it's pretty hard to see. But later on, when the moon does subside, it'll be a good chance to try to see it with the telescope. Or binoculars if you can. It's pretty well almost 7th magnitude now, 6.7. 7th magnitude, which is just under naked eye visibility. 6.0 was the limiting factor of our eyes in the country, a lot less in the city. Next slide. Of course, the grandest of all the meteor showers, the Perseid meteor shower, is on the night of the 12th, 13th. The expected annual rate is about 100 per hour on a nice, clear, dark night. This will be 3 nights after the supermoon, the super full moon. So we should have a waning gibbous moon, so maybe about 60 per hour. But still, there are fireballs associated with this meteor, so with this meteor shower. So you should have a good opportunity to look at some nice little shooting stars, as people generally call them. But unfortunately, it's Tuesday night into Wednesday morning, so unless you're on vacation, next morning will not be nice getting up. Next slide. Okay, a couple of photo ops coming up with Venus and Jupiter. Jupiter has moved now out of the evening sky into the morning sky, and Venus is now moving pretty well out of the morning sky, going into the evening sky very soon. But the 2 brightest planets of our solar system will converge very close together. The unfortunate part is the time. It's very early in the morning, pretty well close to dawn. Next slide. So on August 18th, if you see Venus and Jupiter, you might see the beehive cluster, but being the sky getting light, you might not be able to get it. So try as soon as you can. It's very, very low to the horizon. So that'd be a great photo op for sure. And next slide, please. The International Space Station, of course, has many passes over Ottawa. I do have a link on my website to it, wondersofastronomy.com. But one of the best ones is pretty well directly overhead. It'll be a blazer, about minus 3.3 magnitude, and Venus is minus 4.4. So this will be extremely bright as it comes out of the western sky and then moves into the shadow of the Earth. So, and it's at 8:50. 9 o'clock, about 9 o'clock at night. So that'll be really something to see. So if you want to bet some money with your friends that, I think I can bring to the space station, you might make a few bucks, and I'm in for 10%. Next slide, please. Because I'm the president, that's why, get my cut. The next photo op will be on August 28th, pretty well at the end of the month. And unfortunately, August, now we're getting into September and snow, hopefully not too soon. But Orion will be rising very, very soon. Here we have the moon on almost setting, along with Saturn and Mars. So great, again, just a photo op. Next slide. Of course, my monthly article that I write for the national RASC talks about the Summer Triangle, Part 1, because there's just too many objects to really speak about. And many of the graphics that you have seen tonight will be on that. So you can catch it through the Ottawa Centre website, ottawa.rasc.ca, my website, which I mentioned before, or you can also follow me on Twitter at AstroEducator. Okay, next slide, please. The supermoon or sturgeon moon will be on Sunday morning at 4:09. Well, it says 14:09, it's actually 4:09 Eastern. And because we have 3 supermoons this year, July, August, and September, but this will be the closest. And unfortunately, with what's happening in Hawaii, we're getting 2 hurricanes. Not a great time of year to have a supermoon pretty well on that same weekend. So again, watch the bathtub, watch the hot tub. Don't want anyone drowning with the high waves. And again, just your other for observing purposes. And that's it. Next slide. Great. And that's it for next month for observations. I just add one little point here too, is the success of any group, club, or society falls squarely on the shoulders of a core of volunteers. Without them, many events would never take place or run extremely poorly, as you can tell by Chris Tarrant and Mike, many great people. If these guys didn't do, how many hours you do this week, just get ready for this? Many hours, it wouldn't run smooth. So right now, for these 2 guys. And over the past years, Peter Heyman has given a helpful hand to many, many star parties, museum events, including Astronomy Day, heavy involvement with the International Year of Astronomy activities, and other community events. Well, tonight we say farewell to Peter, as Mike already told you before, as he's leaving for school at McMaster University, just down the road in Hamilton, but he will want to get out of there pretty fast, come back to Ottawa, for sure. So please join me in wishing Peter all the success of his studies and his past contributions to the Ottawa Centre. Thank you, Peter. And I'm out of here. Thank you, folks.
So for the people who are here for the first time tonight, we don't normally clap this much, but thanks very much, Gary. And next up is Al with a 10-minute What's in the News astronomy segment. Thanks.
Thanks, Mike. Okay, so as some of you know, there's been some very interesting developments in the field of astronomy very recently, and I'd like to show you some of the highlights of the Rosetta mission, which has just arrived at a comet. So, I have a little video.
Rosetta Comet Comes Alive, presented by Science at NASA. A spacecraft from Earth is about to do something no spacecraft has ever done before: orbit a comet and land on its surface. Right now, the European Space Agency's Rosetta probe is hurtling toward Comet 67P Churyumov-Gerasimenko. The spacecraft's mission is to study the comet at close range as it transforms from a quiet nugget of ice and rock, frozen solid by years spent in deep space, to a sun-warmed dynamo spewing jets of gas and dust into a magnificently evolving tail. Newsflash, the metamorphosis has begun. Comet 67P is coming alive, says Claudia Alexander, project scientist for the U.S. Rosetta Project at NASA's Jet Propulsion Laboratory, and it is even more active than I expected. Launched in 2004, Rosetta has spent the past few years in hibernation as it chased the comet across the solar system. In January of 2014, with its destination in sight, Rosetta woke up and turned on its cameras. At first, the comet looked like a dimensionless pinprick, inactive except for its quiet motion through space. Then, on May 4th, a bright cloud appeared around the nucleus. "It's beginning to look like a real comet," says Holger Sierks of the Max Planck Institute for Solar System Research in Germany, where Rosetta's OSIRIS science camera was built. "It is hard to believe," he says, "that only a few months from now, Rosetta will be deep inside this cloud of dust and en route to the origin of the comet's activity." Spacecraft from NASA, ESA, and other space agencies have flown by comets before. A whole armada of spacecraft visited Comet Halley in the mid-1980s, an international event which still serves as a touchstone of comet research. Other notable examples include NASA's Stardust mission, which flew through the tail of Comet Field in 2004 and returned samples to Earth 2 years later, and the Deep Impact spacecraft, which in 2005 dropped a projectile into Comet 9P Temple, blowing a hole in its nucleus so that researchers could look inside. Flybys are informative, but Rosetta will do much more. A flyby is just a tantalizing glimpse of a comet at one stage in its evolution, points out Alexander. Rosetta is different. It will orbit 67P for 17 months. We'll see this comet evolve right before our eyes as we accompany it toward the sun and back out again. The most exciting moment of the mission will likely come in November, when a European-built lander descends from the spacecraft and touches down on the comet's surface. The lander's name is Philae, after an island in the Nile, the site of an obelisk that helped decipher, you guessed it, the Rosetta Stone. Because a comet has little gravity, the lander will anchor itself with harpoons. The feet may drill into something crunchy like permafrost, or maybe into something rock solid, Alexander speculates. Once it is fastened, the lander will commence an unprecedented first-hand study of a comet's nucleus while Rosetta continues to monitor developments overhead. Although Rosetta is a European mission, NASA has contributed some important instruments to the spacecraft, and U.S. scientists are just as eager as their European counterparts for Rosetta to arrive. The recent photos have helped mission controllers pinpoint 67P and start a series of maneuvers that will slowly bring the spacecraft in line with the comet in time for an August rendezvous. "Our target is ahead," says Alexander, "and Rosetta is chasing it down." For updates from the comet's core, stay tuned to science.nasa.gov.
Okay, so a really cool mission. Can you advance it? Thanks. A long time in planning. As you can see, 10 years to get to the comet. It was launched in 2004 on a long orbit. Now, comets, the reason scientists are interested in comets, they're considered to be primitive building blocks of the solar system and may have helped to seed the Earth with water, the oceans of the Earth, perhaps even ingredients for life. There's a lot of fundamental questions yet about what they're made of, what their density is. Are they mostly water? Are they dusty? Are they dark? So the Rosetta mission is going to answer some of these questions for us. The comet itself and Rosetta are currently about 405 million kilometers from Earth, about halfway between the orbit of Jupiter and Mars. The comet is an elliptical 6.5-year orbit that takes it from beyond Jupiter at its farthest point to between the orbits of Mars and Earth, at its closest to the Sun. The mission, actually, because it took a long time so that it didn't have to use a whole lot of fuel to get to this orbit to match speeds with the comet. It actually had 4 gravity assists from planets during its attempt to catch the comet, 3 from Earth and 1 from Mars. March 4th, 2005 was its first gravity assist. It then in 2007 turned towards Mars. It imaged the deep impact with Comet Tempel 1 that we saw previously there, en route to Mars. In February 2007, it had a close flyby of Mars, which provided a gravity assist for its second Earth, back to Earth for its second Earth flyby in November 2007. In 2007, it actually flew by Earth, gaining its gravity assist to get it into the asteroid belt, and at the time it was actually imaged by a telescope and identified as a near-Earth asteroid. 2007 VN84. It was identified, its orbit was plotted, it was classified as a potentially hazardous near-Earth approach. It was going to come within 5,700 kilometers of the Earth, which was quite surprising. But then astronomers realized that, oh, this is the space probe we sent out several years ago. And they issued a retraction. On September 5th, 2008, Rosetta passed within 1,700 kilometers of asteroid Steins. Is this on? I don't think it's on. Can you give me the next slide, please? Within 1,700 of asteroid Steins, enabling its instruments to closely observe the rock, flying by at 8.6 kilometers per second. And then asteroid Steins, as seen as from a distance of 800 kilometers, taken by the OSIRIS imaging system for two different perspectives. The asteroid itself is 5 kilometers in diameter, approximately as predicted, and it's got a huge impact crater on it. Scientists, it's a 1.5 kilometer diameter crater. Scientists are surprised that it actually survived the impact that created that crater. In November 2009, Rosetta swung back for a final boost from Earth's gravity to return again to the asteroid belt. Get the next slide, please. On July 10th, 2010, Rosetta flew within 3,000 kilometers of asteroid Lutetia, which is a major asteroid. And again, this one being 10 times larger than Steins at 100 kilometers in diameter. 21 Lutetia is a main belt asteroid of an unusual spectral type. It has an high average density, 3.4 grams per cubic centimeter, which means that it's made of metal-rich rock. And here's a couple different images of it from the flyby. Go to the next one, please. And here's a close-up of the crater on its surface. Landslides are actually visible on the surface of this 100-kilometer asteroid, and they're thought to have been caused by the vibrations created by impacts elsewhere on the asteroid, dislodging pulverized rocks. By May 2011, Rosetta was coasting through the outer solar system, trying to catch up on a slightly smaller orbit than the comet itself, catching up to it, and it went into a hibernation mode to save energy because its solar panels weren't providing enough electricity to keep the instruments running. So it just kept its heaters and its main computer on. And then in January 2014, it turned itself back on, fired its engine to position itself for its rendezvous with the comet. The last of a series of 10 rendezvous maneuvers that began in May to adjust its speed and trajectory came down from 750 to 1 meter per second relative velocity with the comet, occurred in August 6th. So this is really breaking news. So it's positioned itself properly now to do some science as predicted. Go to the next one, please. So here was a July 29th image from the NavCam. And one of the surprising things of the comet was that it looks like two objects close together. It's a contact binary, what they would call. So as it approached, we saw more of the comet. And here's August 3rd image from the NavCam. And you can see there's what seems to be two objects which appear to be connected maybe by a bridge of debris. And then here is a close-up from 285 kilometers away, taken on August 3rd by the OSIRIS camera of the comet itself. So the Rosetta is now 100 kilometers from the comet's surface, and over the next 6 weeks it will fly two triangular-shaped trajectories in front of the comet, coming down to 50 kilometers in the second one. At the same time, the instruments will be scanning, looking for a target site for the lander, and eventually it will close in at a 30-kilometer orbit and may come even closer. The comet itself is 3.5 by 4 kilometers in size, and measurements of the water vapor coming off the surface suggest that it's losing water into its tail at approximately 1 liter per second over the whole thing. So the comet surface temperature is about minus 70 Celsius right now, and ice is basically diffusing out into the vacuum of space at 1 liter per second over the surface of this entire object. So astronomers are thinking that it's probably a dark, dusty object with some permafrost in it that's coming out. And the density is very low, on the order of 1/10 of a gram per cubic centimeter. So there could be voids and it could be rubble. So quite an interesting mission. I'll just leave you with a final close-up of the smooth area in between the two objects. You can see some really cool detail here, and it's going to be very interesting as the comet gets closer to the sun and more gas starts to spill out of it as the probe analyzes it. So a really cool mission. I'm looking forward to some really interesting results from it. Thank you.
So Rosetta's been in the news lately, which is nice, but I have to say we're very fortunate to have Al Scott, who can do these kind of deep dives and dig into this to the extent that he did. And I know that Al was doing some traveling this week, so I have a feeling, Al, you probably worked very hard and very long and probably well into the night doing this. So thank you very much for this. Okay. Next up is Peter Heyman. Subject is black hole lookalikes and where to find them. Right up his alley as a physics student.
Peter.
Hi, folks. So, I think the last time that I was up here was several years ago, and I was showing some astro photos. And so since then, I've actually gone and thrown all of my telescope money at a degree in physics. So I figured before I go and throw some more telescope money at another degree, I thought I'd maybe try and use that degree to sort of paint a different kind of picture, perhaps. So I'll give you a little introduction to black hole analogs. So the first thing that we'll need is some motivation for this topic. And the first motivating point, of course, is black holes are really cool. Okay. If they weren't cool, this would be pointless, no one would care. But they're really cool objects. But the next 2 points are where this gets a bit dicey. You see, your average free-range black hole will roost somewhere between a few light years to the edge of the observable universe. So it's generally what we tend to perceive as telescope distance. However, they're also usually defined pretty much to be precisely the sort of thing you can't see with a telescope. So we have a bit of a dilemma here, and one solution that has been proposed is to make things that are kind of like black holes on Earth and see if we can test theories and ideas about black holes in a lab. So before we can come up with a fake black hole, we've got to be clear about what we mean by a black hole. Now, formally, a black hole is a vacuum solution to Einstein's field equations of general relativity, when you have certain initial conditions like mass and charge, and you have certain symmetries like spherical symmetry and whatnot. But I mostly mention this just because right here in this definition is probably my favorite point about black holes, which is that they're a purely geometric phenomenon. We tend to talk about them like they're an actual object, like stars or galaxies or whatnot, but they're really not. There's nothing there. They're just the shape of space itself, which I think is really neat. But for our purposes, we'll need something a bit more practical than this. And so we'll basically just talk about things that are characterized by having an event horizon and possibly a singularity if you feel like it. But it's mostly the event horizon that's important. And we'll define this event horizon in terms of allowed trajectories. It's a sort of vague way of looking at it, but it'll be useful. So there are sort of two different types of trajectories that you can have. And we'll define the event horizon in terms of external trajectories. So trajectories that begin outside of the event horizon can either end within it or also outside of it. However, trajectories that begin on the inside of the event horizon have to end on the inside. And you'll notice this also precludes any trajectories that pass through the event horizon, because they would pass through the black hole, because they would have to have a segment that begins inside the event horizon and ends outside. And also another property that's fairly characteristic of event horizons is Hawking radiation, wherein gravitational energy of the black hole is sort of emitted in the form of radiation. But that doesn't really fit in with the trajectories. All right, so the first analog that I'll bring up is a fairly straightforward conceptual one. And this is also one you can do at home, but this isn't the one that I promised you, because this is pretty dull. We all know what the bath tornado is, right? You just fill up a bathtub and drain it. But this is a two-dimensional black hole. And you can see this by the help of these kind rubber duckies. So if you have a draining bathtub, you can place objects in the tub and they can follow some trajectories. Some trajectories will pass a certain point, and from that point, anything you place there will fall into the vortex. But there are also places you can put a rubber ducky where it'll swing by the vortex. Obviously, the actual bathtub is not it's a dynamic system, so this it won't stay like this. Everything will fall in. But if you had something that's a much larger bathtub, something where the water is resupplied, you can have a sort of stable system where you can have trajectories where things actually miss it. And Earth has a few of these giant bathtubs. One of them is the South Atlantic Ocean, where there actually are these little drains, these eddies and vortices. And just to let you know that this isn't just a frivolous analogy here, there's a paper here where a team actually used the differential geometry of general relativity to identify and track whirlpools in the South Atlantic, these self-contained coherent vortices that transport material across the ocean, material and water. So here we actually have general relativity, the mathematics of gravity, finding an application tracking whirlpools in the South Atlantic, which is really neat. And the next one I'm just going to sort of fly through because I only really picked it up because there's a really neat application, quote unquote. And this is the optical analogy. And in this, what you have is you have a material where you can change the index of refraction. They're metamaterials, and you can set up geometries of different indexes of refraction. And this is the index of refraction of a material determines how light will bend when passing through it. So if you vary the index of refraction to a certain point, you can force light to behave pretty much as if it's passing by like a space-time vortex or something like a black hole. And you can see in these simulations that you can actually do something really quite similar to this. But I really only mention this because I did come across a paper that suggested an application of these, and it had pretty much the most sci-fi name I've ever seen in an actual scientific paper, and it's optical black hole lasers, which I think just sounds really neat. I don't know what you could use it for. I don't even really know how it works, but those pictures are cool and it sounds really neat. Now, there are many more applications, like there are loads of analogies that you can use. But the last one that I'm going to bring up is one that I think is pretty much the kicker, and it's actually the first one that I came across. And this is the condensed matter analogy. Now this is where you can set up an analogy to a black hole that actually has a lot of analogous points. And you have to do it in a Bose-Einstein condensate. This is, not to get into too many details, it's a macroscopic object that behaves like a quantum object. So you have full access to quantum theory, but you also have the accessibility of a macroscopic object that you can play around with in the lab. And researchers have actually set up a black hole analog using this stuff. Now, it's not much to look at here, but what we have here is a Bose-Einstein condensate, which is, in this case, it's a fluid of quantum particles. And in the analogy, the speed of the fluid basically is sort of like the curvature of space-time. And the speed of sound waves in this fluid is equivalent to the speed of light in real space. And the equivalence is actually quite deep, particularly because this is a quantum theory. And what we have here, especially if you see plot G over here, the red plot is the velocity of the fluid, and the black plot is the speed of sound in the fluid. And you can see that black dot where they overlap is an event horizon. So you can have quanta of sound, which would be phonons. It's equivalent to a quantum of light, which is a photon. They can start from the right side of this and travel through to the left side, but you couldn't have a sound wave start to the left and travel to the right. Now, actually, there's also another type of horizon to the left marked by the cross, which is a white hole horizon, and I'll get to that in a second. But what's really interesting about this particular analogy is because it is a quantum theory, it's also possible to observe Hawking radiation with this, which I mentioned was a part of one of the key aspects of a real black hole event horizon. And the researchers who did this experiment have mentioned that they're very close to being able to observe Hawking radiation with it. The Hawking radiation temperature is just about an order of magnitude lower than they were able to observe, but with modifications, it's possible that they can actually see this, which would be one heck of a first. Because with your average black hole, the temperature, the Hawking radiation is actually cooler than the background radiation of the universe, which is, I mean, you're not going to see anything if you're wiped out by the rest of the universe. All right, so now I'm going to get to the one that you can see at home. And I kind of lied, it's not a black hole, but it is a white hole. And to get a white hole, all you really have to do is run time backwards on a black hole. So with our trajectories definition, you just take the arrows from the end and put them at the start. And you can do this in general relativity and in quantum field theory because they don't set up a direction to time. You can flip time back and forth however you like. All right, so where can you find one of these things at home? Well, the first thing that you have to do is you have to head over to a tap, and then you have to turn it on. And you have yourself a white hole. That circle there is an event horizon. What's happening here is the speed of the water inside that circle is greater than the speed of waves in the water. That circle marks the boundary between where the speed of the water is the same as the speed of waves in the water, and then outside of that, the speed of waves in the water is greater than the speed of the water itself. And this has been looked at by real scientists, actual smart people, including Dr. William Unruh, who is a Canadian physicist and a pioneer in the black hole analog field, and also has an effect named after him, so, I mean, he's automatically awesome like that. You can see in the top picture there, he is making a kitchen sink white hole, but he's making it in a cross section, so you can see right where the white hole boundary forms. He's got a variable speed, variable flow rate for the water. To the left, the flow rate is faster than the speed of waves in the water. That boundary there marks where the speeds are the same, and then to the right, the speed of waves is faster than the speed of the flow. And this has also been measured another way. Another team used silicon oil to produce their own kitchen sink white hole, and they measured Mach cones, where you put an obstruction inside that event horizon, and you measure the angle that that pattern makes, and that angle is proportional to the ratio of the speed of the flow to the speed of waves in the medium. And they actually did this scientifically and took a series of measurements, and they determined at the boundary your speeds are equal. Inside, the speed of the flow is greater than the speed of the waves, and outside, the speed of the waves is greater than the speed of the flow. So you head home, turn on a tap, and you're making a white hole. Thanks.
Does anyone have any questions or anything want to comment on it? Although, and for those who know, I've been working with Peter for many years, so if you could, and I've been doing my utmost here to try and embarrass him or whatever tonight, but if you could preface your questions with deep skepticism. Sorry, go ahead. Matthew?
Just the literal words, deep skepticism?
Yes, absolutely.
Deep skepticism. The fluid dynamic analog you had was this spinning vortex of fluid.
Yes.
And the analog of whatever is trying to go into or out of a black hole was the rubber ducks. But in an actual black hole in space-time, a property is that however one forces the motion, it can't leave the black hole, yeah?
Yes.
But if I strap a rocket motor to a rubber duck,
Yes.
or even if I strap a propeller to it.
No, that's the thing is you're changing, like it destroys the analogy when you change the environment like that. Because having like a motor on top of a rubber duck is sort of like having an intense mass or something seriously warping space-time in the actual black hole situation. When you have when you're actually modeling black holes, the mass and energy in the system is how the geometry is warped. And usually you don't take into account the mass of any observer that you're talking about because it's vastly smaller than anything else. But if you do have a non-negligible mass in your observer, it causes a back reaction, and you have to take it into account when determining your metric.
But
So
I mean, I mean, not the mass of, for example, if we have some craft falling into a black hole and it's thrusting outward, what would the analog be in the fluid dynamic analog? Would it be a propeller in the water itself?
Not sure what you mean.
Well, if we have a craft falling into a black hole, it can thrust outwards, it can have some motor.
Yeah, it can thrust outward, but the energy that it's going to be using, it's still not going to be significant on the mass energy scales of the black hole. If it were, you would have to take it into account when determining your geometry, and it could change things up. So these analogies are actually assuming you're observing particles don't distort the analogous geometry of the situation.
And that's purely an analog of spinning black hole.
No.
No?
That's an analog of a static black hole, of a pretty much a Schwarzschild.
But how so? As if we leave a rubber duck just somewhere about the vortex, it starts moving with.
The velocity field of the water is the analog of the space itself.
Yes.
Maybe we can.
Yeah.
Sorry.
Talk after.
Yeah, I think
Yeah,
there's actually
I
an
think-
add-on question over there.
Yeah.
Really loud, please.
Peter, is an event horizon a perfect shape?
No, not necessarily. It depends on the properties of the black hole that you're talking about.
Could it be on Is that what you're saying then?
It could be oblate if you have. It's either if you have charge or angular momentum. There's a sort of double boundary. It gets kind of weird, but in your standard Schwarzschild case, where you just have mass, it's just a massive black hole. There's no spinning or anything. Then it's just a perfect sphere.
Okay.
How about in the back there?
Peter, just
Really loud, Rob.
okay, you, in the water coming onto the sink, that's essentially your event horizons, where the water changes from supercritical to
Yes.
subcritical flow. It's essentially a shock wave.
Yeah.
So is it appropriate to extend that even to an aerodynamic shock wave?
Yes, absolutely. Yeah. Okay.
Just a question about the condensed matter paper. Do they generate the condensate through cryogenic research?
Yeah. It was
laser?
like a couple of Kelvin rubidium atoms. Yeah.
We got to cut it here.
Okay.
Sorry.
Okay.
Thank you, Peter. Well done, Peter. It's a tough subject to take on, so congratulations on that. Okay, Prajesh is going to talk about the Star Party program we had and the Star Party, the public stargazing session that we had just recently. So, Prajesh.
Good evening, everyone. So yeah, we just had our first star party for the Ottawa chapter last month, and it turned out to be quite a success. We had 26 scopes in total, so I'd just like to send out my personal thank you to all the volunteers who brought in their scopes. It was amazing. We also have a little, our next upcoming star party is on the 16th, the 15th, sorry, 15th. The rain dates will be on the 16th, so the Saturday following, or the Friday next week after, or the Saturday, depending on the clouds. And it'll be hosted again at the CARP library over here. You can go to our website at ottawarasc.ca to find directions as well as other information. The start party does say it starts at 9 p.m., but if you'd like to come set up at 7:30, that'd be highly appreciated. If you guys are new to stargazing and you would like some help with setting up your scopes, please arrive ahead of time too. We have lots of people who are willing to help out. And yeah, we have 2 more star parties going into the fall. So once in September, once in October. The first date set here is the date we are aiming for, and everything else is the subsequent rain dates after that. And yeah, we also have a short time lapse by David Woods, so I'd like to thank David for this clip here.
Don't touch it.
Oh.
Something's wrong. Just a sec.
So yeah, that was pretty cool. Yeah, and I'd hope to see everyone there next week when we have our starter party again. If you guys have any questions, I'm available during the break.
Yeah, just to add to what Rajesh has said, these public star parties or stargazing sessions are open to anyone. You don't have to have a scope to attend. You invite your friends, neighbors, colleagues, and hope you enjoy the evening. I think our club does a fine job. There's also other allied astronomy groups that come to these events as well, and we welcome everyone. All right. So I want to mention something else. We're very fortunate to have our stargazing sessions at the CARP Library, which is, as Rajesh has said, right adjacent to the Diefenbunker site. In order for us to use that site, we had to have it's City of Ottawa property. We had to have explicit approval from the CARP branch of the Ottawa Public Library. So they've been extraordinarily supportive of us over the years, and they've done some things to help turn off the lights in support of our events. And I can't tell you how grateful I am, because without them doing that and without them supporting this, we wouldn't have had these wonderful events. They are asking for our help. Okay, they have an event. It's a fundraising event coming up Saturday in a week, and they've asked if we could set up our solar scopes. So I'm sort of putting out a desperate appeal. If you can, this will be an event that'll go from 12 to 3. If you can support just a couple of hours of your time, please come see me today. I will be sending out emails calling for support, but I'm looking for about a variety of different solar scopes, white light, AH alpha, and so forth. But this is an important event, and I really want to show our thanks to the CARP Library. Okay. So just before we go to our break, a couple things. For those new members or people who are new and considering membership, we do have a number of benefits, one of which is a very popular telescope loan library. So as a member, you can sign out telescopes. If you have telescopes on loan, and Al Scott, who you saw earlier in the 10-minute astronomy news segment, and want some help, let Al know, or let myself, or you can almost speak up to anyone here tonight. We can do many things, such as come to your place. Maybe you could come to our place. Maybe you can certainly come to the star parties. We're happy to assist, because the last thing you want to do is give you a telescope and you figure it out yourself. No, we can do more than that. All right. We do have an observatory also available to members, and in order to use this observatory, you have to go through a quick course, and you have to have a key to the observatory. Now, Ron St. Martin, I know you're probably sitting back there, right? He's got his arm up there in the back, so keep your arm up for a second so people can see. So if you're a new member and you want to know about he's standing up right now, thanks. You want to know about how to get he's dancing. Okay, you can the arm is fine, thank you. Please see Ron, okay, because I think this is a great benefit, and there's a lot of people who use that observatory, so wonderful. Okay.
I just want to add that I will be having another training session either near the end of September or early October.
Okay, and it's a year-round observatory, because there is they plow the site of snow and so forth. So it's well run, and I think it's a nice benefit for new members. So If you're a new member, you're considering membership, we've got these kinds of programs to sort of assist you along the way. Next. There's a couple of journals, and all these benefits are on our website and on the national website, rasc.ca, which is where you sign up. Next. Something I wanted to mention, it was brought up by somebody recently, which is a fairly new. So regular membership, regular in the sense of an adult, over 21 years of age, is $72, okay? There's a new membership that just popped up recently, and it's a family membership. So if there's a base charge of $67, okay? Well, Chris, you're gonna have to correct me if I'm getting this wrong here. The second adult, the first adult would be $10, so that would be $77. The second adult would be $87, okay? And youth is a $5 adder. So basically, for $87, two adults could become members. So thanks, Martha, for reminding me about that, and Chris also for reminding me about that. I think this is the way to go if you're considering it. Okay. Okay, what we'd like to talk about, something else we'd like to talk about just before we resume with the rest of the program here is our annual dinner, and Gordon is going to say a few words, so please.
Okay, everybody open the calendar app on your smartphones. November 14th is our annual dinner. That's a Tuesday night, just for a change. No, just kidding, it's still Saturday night. Friday? It's Friday night. Yeah. 14th anyway, I know that for sure. Tickets will be the same price as last year, $42. And we're working on a couple of high-profile people for the speakers. We hope to have it finalized for next meeting. Okay? Thanks.
Thanks very much. Let's go to the next slide. Okay, the next, I'm delighted to welcome Bianca August to talk about impact craters and what they mean to us on Mars. Bianca, thanks for coming.
Good night. My name is Bianca Deru, and I'm currently a master's student in geology and planetary science at the University of Western Ontario. I'm also part of the Center for Planetary Science and Exploration at Western, and I'm studying under Dr. Gordon Siski and Dr. Livio Tarnabene. So I'd first like to talk about the various reasons of why we study impact craters. Fundamentally, we study impact craters to understand the impact cratering process, but we also seek to understand the Earth's past geological history, the biological history of the Earth, as well as of other planets, the history of our solar system. And surprisingly, impact craters do have an economic significance. There is the copper-nickel mine in Sudbury, which resulted from an impact crater that hit the Earth 1,850 million years ago. A few pictures of impact craters. The most famous simple crater on Earth is the Beringer or Meteor crater in Arizona. We have the Chicxulub crater off the Yucatan Peninsula in Mexico, which led to the mass extinction of the dinosaurs 65 million years ago. We have a few craters that have been studied by the CPSX research team at Western. We have the Mistaston Lake impact structure in northern Labrador, which is also a premier lunar analog site on Earth because of the presence of shocked anorthosite, which is the main type of rock found on the Moon. We have the Slate Islands impact structure in the Lake Superior. We have the Rise impact structure in southern Germany, which is also the best preserved complex impact crater on Earth. Now, in the solar system, we have Herschel on Mimas, which is one of Saturn's moon, and Tycho crater on the Moon. Finally, we have the Elas impact basin, which is the biggest known impact crater in the solar system, with a diameter of 2,300 kilometers. Now, for comparison, the Chicxulub impact crater that led to the mass extinction of the dinosaurs has a diameter of 180 kilometers, and this one has a diameter of 2,300 kilometers. And it pretty much covers, a big part of the southern hemisphere of Mars. As a side note, I'd like you to notice the striking dichotomy that you observe on the surface of Mars. You have the southern hemisphere, which is heavily cratered and much higher in elevation than the northern hemisphere, which is very smooth and much lower in elevation. And if you look at the left globe, at the equator, you have the biggest known canyon system in the solar system, Valles Marineris. And in the northwest, you have 4 shield volcanoes, with the biggest one being Olympus Mons, so this one here, with a height of 25,000 meters. Now, types of impact craters. I've mentioned simple craters and complex crater. So these are the 2 main types of impact craters. But you also have multi-ring and basins, which are much bigger. And those types of craters vary according to the diameter. So simple craters are the smallest craters, and they are characterized by a bowl-shaped depression, which we call a transient crater. So the bowl-shaped depression that pretty much characterizes the crater is called a transient crater. As the diameter increases, you get complex craters, which includes the multi-ring and the basins. And complex craters have a central uplift, so a centrally uplifted region in the center of the crater that exposes deep subsurface material. On Earth, the transition from simple to complex occurs between 2 and 4 kilometers, and on Mars it occurs between 5 and 10 kilometers. And this is governed by the planet's gravitational strength. A good example of a simple crater on Mars is Zumba. So as you can see, you have this very simple bowl-shaped depression called the transient crater. But on the right, we have Alga, which is the first crater that I'm studying as part of my master's research. And this is a picture of the central uplift on Alga. Now, this is a figure showing the morphological and structural differences between simple and complex craters. The simple crater, you can see you have the fractured bedrock in the basement, and the transient crater is coated by impact melt and breccia, which is a type of rock. And on both sides, you have ejecta deposits, and ejecta deposits is the material that was ejected out of the crater at the time of the impact. Now, if you look at complex craters, you do have your depression, but it is a bit more shallow because of the rise of the central uplift. You have your basement, which is highly fractured, with the transient crater, the depression being coated by a sheet of impact melt. And then on both sides, you have ejecta deposits, and you have the crater rim here, which is quite different from the simple crater because actually these are called terraces, and they resolve from the collapse of the crater rim. So what happens is that you do have a simple crater, but as the diameter increases, the craters become unstable. And when it becomes unstable, you have the collapse of the crater rims, and because of gravitational adjustment, you have the rise of the central uplift. So once you have your rims that are collapsing, your central uplift rises, and that's what we understand for up to now. When it comes to studying central uplifts on Mars, we follow, or we do 3 types of mapping. We do morphological mapping, structural mapping, and spectral mapping. And we use a lot of data. The latest orbiter that was put in orbit on Mars is the Mars Reconnaissance Orbiter, 2005. And on this spacecraft, we have the high-resolution imaging science experiment, HiRISE, which provides satellite imagery at 0.25 meter per pixel, which is, I think, much more precise than what we have on Earth for now, if I'm not mistaken. We have the context camera, CTX, which provides regional imagery at a scale of 5 meter per pixel. And we have the compact reconnaissance imaging spectrometer for Mars, which provides spectral data. And we also have another spacecraft, the Mars Global Surveyor, put in orbit in 1996, which provides digital elevation data for Mars, which we call MOLA, so the Mars Orbiter Laser Altimeter. Now, this is a map of Mars with about 170 craters compiled by my supervisor, and these craters expose these craters have good exposure of central uplifts. Now we categorize central uplift on Mars according to bedrock. The first type of bedrock is layered bedrock, and it's mostly found in volcanic provinces on Mars. But we also have the fractured massive type of bedrock, and we have megabrecciated bedrock. And we also have mixes of the different types of bedrock. Now, the first crater I'm studying is Alga, and it's found southeast of Valles Marineris, which, like I said, is the biggest known canyon system in the solar system. And this is a CTX imagery of Alga. You can see the crater rim with the central uplift in the middle. And it has a diameter of 22 kilometers. Again, this is a 3D model of Alga created in ArcGIS. Okay, so the first component of the mapping is the morphological and structural mapping, and I'm doing this in ArcGIS. Now, what's important to understand is whether you have something that was formed before the impact, at the time of the impact, or after. Now, the bedrock that you see on any craters can be pre-impact or at the time of the impact. For example, Alga is actually situated in a bigger crater called Chequelin. So the bedrock that you see in this central uplift could actually be the bedrock from the crater below. But we don't know that yet, but we're trying to understand and we're trying to find out what's actually happening here. And we also do structural mapping, and when it comes to structural mapping, we try to map fractures, dikes, and veins, and these are mostly sin impact, so they probably were created at the time of the impact. But we also have post-impact deposits such as dunes and mass wasting features on Alga that were formed after the impact. Again, this is a 3D model of Alga, and the red rectangle here shows a key region on Alga, which exposes all the deposits that you see in, like, if you look at the whole crater, all the deposits that have been recorded are found in this very small region. So you have the fractured massive type of bedrock here, which is overlain by dunes. You have class 4 impact melt, class rich impact melt, and you have this class here, which is quite unusual. And this might be a surface that is actually coming from the crater below. We're not sure yet. But this could be something that was uplifted and then a little bit of erosion, and that could belong to the crater below Alga. Again, a 3D model of Alga, which is overlain by spectral data. Now, what you see in red is olivine. What you see in cyan is a mix of low calcium pyroxene and high calcium pyroxene. Well, if you look at the legend, actually, you have green, red, green, and blue. So green is low calcium, blue is high calcium pyroxenes. But since you see cyan, well, it's a mix of blue and green. Therefore, you have a mix of the two minerals. And to do a really good study of a crater, you need to combine morphological, structural, and spectral mapping, and that's what's lacking in the Mars community right now. You see a lot of people who do morphologic and structural mapping, but you don't see a good combination of spectral and morphologic mapping. So it's a good thing that we're seeing a lot of mafic minerals on Alga, and we're hoping to, I'm hoping to continue my mapping and get more results and actually understand what's happening right here. Why are we seeing this class? My next target could be a crater in the northern hemisphere of Mars, which depicts colorful uplifted rocks. I'm not sure if I'm going to map this one, but I have about 3 impact craters to map in the course of my master's research. And yeah, that's about it.
So we have time for some questions as well, or perhaps somebody wants to add on some suggestions for research as well. I saw a hand go up. Really loud.
Yeah, the fractured massive bedrock, the spectral mapping that you did suggested it's a basaltic composition, but you don't think it's volcanic. What are these intrusive rocks?
Alga is not in a volcanic province. It is in a region characterized by. It is in a region where you have Noachian terrain, and Noachian is the oldest. Well, it's the oldest period when it comes to the history of Mars, and the volcanic provinces are really mostly in the northwest, and you have a region in the northeast of Mars when you have a lot of volcanic rocks. Therefore, well, yeah, it's not volcanic rocks. Mm-hmm. Yeah.
Yeah, and the complex craters, there's that central part that comes up.
Mm-hmm.
Like, how soon does it take, or how long does it take for that to come up? Is it right after the impact, or over a number of years, or?
Mm-hmm. You have.
Question?
Mm-hmm.
Could you repeat the question?
Yes.
Yeah, and the complex craters, there's a central sort of a peak that comes up. I'm just wondering how soon after the impact it comes up.
Okay, so the question was, how soon do you have a central uplift that rises from the impact? It can be a matter of seconds, up to a minute. It's very, very fast. You have three stages when it comes to impact crater formation. You have the contact compression stage, you have the excavation stage, and then you have the modification stage. The modification stage can be millions of years because impact craters are constantly modified. But yeah, when it comes to the central uplift, it's like after a few seconds of the impact, everything just goes so fast. Mm-hmm.
Any other comments or questions? Frank?
Can I just ask, how stable are the uplifts after they're created?
They're pretty stable. After the excavation stage, like I said, you have the modification stage, and what you're going to see is maybe some dunes on top of the craters. Maybe you'll have mass wasting features that can modify the crater, but the uplift is pretty stable after that. Mm-hmm. Because actually, the central uplift is a result of the gravitational adjustment once the crater rims collapse, so that's why it's stable after that stage.
Simon?
The Lunar Reconnaissance Orbiter photographs from the Moon clearly show that many of the central uplifts are just gigantic rubble piles,
Mm-hmm.
totally chaotic.
Mm-hmm.
Are you expecting to manage to actually map coherent geology in these uplifts on your Martian examples?
Mm-hmm. Well, what happens in the central uplift is everything, you have a lot of material that is brought up and it's all vertical and it's all mixed up within the true center of the central uplift, right? But then you also have, I'm looking at the crater floor as well, so I have the central uplift, which, it's kind of complicated to understand, but you have the crater floor and you can map some stuff. And then you also have outside the crater rim, you see some exposures, and those exposures could belong to the crater below when it comes to alga. It is a tough job, but the goal is to map as many craters as we can, so we can actually figure out what's happening. We have, I don't know how many craters we've mapped up to now, but detailed morphologic mapping in our team, I don't think we have more than 5 craters. So the more we map, the more we can compare results and actually try to figure out what's happening. And especially combining the spectral mapping with the morphology and the structural mapping of craters.
Okay, right at the back, Rob?
Yes. I have a question regarding the accumulation and then the wasting of sediment on the uplift. Does that affect the spectral features at all?
So the question is whether accumulation and mass wasting features on central uplift actually has an impact on the spectral data, and especially the dust. Yes, it does, and you do have to consider that in your analysis. A good thing to include is, I did not mention this data set, but it's the THEMIS data sets, which provides you day and night infrared data. And you have to look at those data when you do spectral mapping, because there is a lot of dust. Mm-hmm.
Okay. Probably could take one more question. We're going pretty fast tonight, which is awesome. Okay. Thank you.
Thank you.
Bianca, thanks for sharing your work and your time, and thanks Tony Peterson as well for making this recommendation to us. It's through recommendations like this and through just people giving me some suggestions on what we can have. We can have as presenters that these kinds of things work out. So awesome, and keep those suggestions coming in. Okay. All of the presenters, if you could come right up to the front here, so we can go one after the other. First up is Bob Hillier. We need to twist Bob's arm to give us another update on his observatory, and maybe even get a remote demo one fine evening.
That'd be cool.
So this first image that I wanted to show, 14 years ago, I took a quick cam camera, $79 little black and white camera, and I put it on my telescope. This is the first image I took. It's not really that detailed. It's not in terribly good focus, but it was my first digital image. Number of years after that, go to the next slide. Number of years after that, I bought a DSLR camera, a Canon 20D, and I had significantly improved my ability to focus. And this was the same image, and it was in much better detail. The reason I showed these two pictures was to show that when you first start out in astrophotography, your results are not going to be anything like you see in the magazines. And you shouldn't get disappointed. You just need to look at your result and say, so what can I do to improve that, and continue to work at it. And then several weeks ago, next slide please. Several weeks ago, I took this next picture of the same object with an ST4000 XCM camera. And it's quite a bit deeper. This was 17 600-second exposures. And it's quite a bit deeper. The stars are much rounder. And I have been working on my technique a great deal. What I really need to now work on next is the image processing side. I know there's a lot of nebulosity on the left and the right-hand side of this image. It doesn't show up on the screen here, but there's a lot of faint nebulosity there, and I just need to figure out a way to process this image so I can bring out that detail. But I wanted to show the contrast from the early pictures right through to these final pictures, where you have to continue to work at it to perfect your images. You don't produce the magazine pictures the first time, so don't give up on your first time.
Okay, next up is, I think, Paul.
Bob, it's not your processing. I just saw it on the screen there. It's our projector. It doesn't have quite the brightness that that a monitor will have. So yeah, I saw your image, and you've got the extended lobes there. No problem there. It's just, yeah, it's what we're working with there. So don't be hard on yourself. All right, hi everybody. I've got a few things for you tonight. Just start out with this one. In the greater structure of the universe, when we look out at a large scale, we know that that the universe is comprised of many superclusters of galaxies, so conglomerations of hundreds or thousands of galaxies. And in our summer sky, we have some nice examples. This is just a computer plot of the galaxies from the PGC catalog. Up in Hercules. So in Hercules, we have actually, some people say it's two superclusters. Other people say that it's sort of, they're all connected there. But the northern and the southern supercluster. And you can see that, again, all of these are just galaxies. So we've got the northern cluster. Where's our laser here? Top light there. Yeah. So the northern cluster is about 400 million light years from here. This is quite a distant object. And the southern cluster is a little bit farther away. It's about 500 million light years from here. So my first image is of this object here. I focused in on Able 2151. And Chris, if we can get that slide. So yeah, these are very distant galaxies. As I say, they're about 500 million light years from here. But you can see that there's a lot of interaction here. A lot of them are packed pretty close together. You can see some nice interacting examples throughout the field here. And if we look at what you're seeing on the field here versus stars versus galaxy, if I can show the next one there, Chris, those are all galaxies. So just in the one field, there's 116 galaxies from Able 2151. Yeah, it's an interesting collection of objects. They're faint. You need a good night and a fairly good scope to be able to see any of these. The largest one of these galaxies, when I'm talking like this guy or perhaps these guys here, they're only about 1 arc minute across. So about the same size as, you know, Venus through your scope, but nowhere, of course, near the brightness there. So yeah, if we can remove the circles there. To get this image, I shot this with the my 11-inch Edge HD with an Orion SSPV2 CCD imager, and it's about 3 hours worth of exposure. You got to go pretty deep to get these little guys there. But interesting object, and it contains one of the interesting things about this whole cluster is that it contains examples of, you know, spirals, ellipticals, lenticulars. There's a whole the whole zoo is in there. So yeah, quite an interesting object to image. But you definitely need halfway decent conditions because they're pretty faint and they're pretty small.
Paul?
Yes.
That field of view is what, about maybe half the moon diameter kind of thing?
Approximately, yeah. Yeah, it's pretty small. Yeah, that was I was running the 11 at prime focus with that chip. All right, next one. This is a test shot that I did actually last winter. I was evaluating Rock Mallin's Mallincam universe, and so what I did is I took a color shot. This is the Monkey Head Nebula up in Orion. It's right up near Orion's club there, between that and one of the feet of Gemini. And I just amalgamated the color data from Rock Mallin's universe camera with luminance data from my monochrome QHY9 monochrome imager, and just merged them together to see what I could get. So it was an interesting result. It wasn't a very deep exposure. If you go deeper on this particular object, you get a lot more extended nebulosity, which you can just kind of see there. But I kind of like this level of exposure because it sure shows the nebula's moniker quite well. You can see the monkey head. Yes, especially for you there, Brian. I know you like to see faces in these things. So this is in total. This is only 20 minutes worth of exposure. Next one, please. So that's the bubble, and I just shot that actually about a week and a half ago. We've had terrible skies here, even when it's been clear. We've had a real issue with smoke particles in the air. NASA published a really cool image about a week and a half or 2 weeks ago, showing the smoke trail from the forest fires up in northern BC and Northwest Territories being drawn down by the jet stream all the way across the prairies and, of course, right overhead. So in case you've been wondering why the sky, even when it's clear, looks kind of milky white instead of blue, that's your answer. Fortunately, now we seem to be getting past that, but yeah, unfortunately, when I shot these guys, it limited how deep I could go with this, because you can shoot this nebula and get a lot more of the finer nebulosity, but still turned out half decent. I'll try it again in the fall.
Don't be hard on yourself. It's just a projector.
Yeah, I know. Thanks. You're too good to me. So in total, this was actually done with again with the 11-inch Edge HD and Canon 60DA DSLR camera, 9 subframes. I shot this over 2 nights there to try to get the best possible images there, but it's only about an hour of exposure in total. So I picked the best frames and stacked those. But yeah, it didn't turn out too bad. Got the colors of some of the stars there, and certainly the bubble is really cool. It's 11,000 light years from here. So it's a long way away. It's in Cassiopeia, and the bubble itself is like 10 light years across. So this is a big, big bubble. Yeah, quite an interesting structure. Last one I have for you. The summer. Summer is waning. What I think of the summer: Sagittarius, the Milky Way, and lazy days by the Lagoon Nebula, sipping a pina colada. Right. So yeah, you can see the Lagoon Nebula there, the Terrifid, and the globular M22 up there. This I actually shot the night after our last meeting. If you remember our last session, it actually turned quite clear that evening. I didn't have a lot of time by the time I got back out to my corner of God's country there. So I just I took out the 60DA and put it on a star tracker. And so this is a single 90-second exposure, no stacking or anything. Very little processing actually as well. You can see a bit of air glow starting to form near the bottom there, and it was just at around the time that the sun was starting to bring up some dawn light there. So, but it didn't turn out too badly. So yeah, enjoy the summer while you can. Hope you get some imaging in. For those of you that are going to come to Starfest in 2 weeks, I'll see you then. Hopefully we'll get then in 2 weeks what we're going to get for the next 4 days, which is clear sky. What are the chances of that? Anyway, we'll see. So hopefully we'll see you. We'll see some of you at Starfest, and the rest of you, I'll see you next month. Thank you.
Thank you, Paul.
You're welcome.
Gary.
Thank you, Mike. I am back. Just one image. This is from the nice conjunction we had of the Moon, Mars, and Spica. This is actually the transmission tower for my Express ExploreNet internet, the big tower over my roof. So I figured I just happened to stand in front of it and got a shot, so I got the actual unlit part of the moon in with the shot. Because if you overexpose everything, you wouldn't see it, and if you underexpose, you probably wouldn't see these objects. So again, I like to always speak in 3D. The moon is 1.3 light seconds. Mars is about 10 light minutes, and Spica 261 light years. Give you a little 3D image. Thanks, folks. See you next month.
Thank you, Gary. Jim.
Okay, this was a collection of solar images from the same day. I believe it was on the 31st of May, one of the rare days in May that we had sunshine. And it's all taken with two telescopes. The top three and the bottom right-hand corner was all taken with a 98 millimeter refractor and a Herschel solar safety wedge with a number of different filters added, calcium K, the solar continuum from Bader, just an IR cut filter for the visual, and then an infrared high pass. And then I also used a Lunt 35 to get the two hydrogen alpha shots. And I just thought it was an interesting comparison. One thing that I did find is focusing with the infrared pass was much, much easier because it settled down a lot of the bad seeing. And the calcium K was hard to focus, but it did bring up more detail around the limb. I'm continuing to do more testing, and you'll see some images later with some even better results. Next, please.
Jim, I'm not familiar with the solar continuum. What does that offer, the filter?
It's a very narrow bandpass in the green spectrum, basically in the middle of human eye response. And it's supposed to highlight granularity and detail around sunspots. I've had limited success with it, to be honest. I've gotten much sharper images just using a UV IR cut filter. But other people have had good luck with it. It's made by Bader Planetarium. Next, please. This is a shot of the 4-day-old crescent moon taken on the 1st of June. It was actually taken at about 2 in the afternoon using an IR high-pass filter and that same 98 millimeter scope. The IR pass filter cuts out basically all of the visual spectrum. So this is all just reflected infrared off of the moon to really give a sharp, high-contrast image during the middle of the day. And it always amazes me how much infrared that is. The exposure time with the infrared pass filter is the same as with visual band, so it's a lot of infrared.
I guess what it's doing, it's actually chopping out all the predominantly blue atmospheric scattered light.
That's exactly why I'm using it, both for cutting out the blue sky, but also for cutting out the distorted spectrum having to pass through the atmosphere, so there's kind of two advantages to using the IR pass.
How long is the exposure?
Oh, let me think. It was on the order of...
Maybe 100th of a second, or?
No, yeah, it was more like a 1/300th. I'm not sure what that is in milliseconds. My camera is in fractions of a second, not milliseconds. So like 3 milliseconds, 4 milliseconds.
Did you get any stars? Would that be a star?
No, that's probably a defect, yeah.
Can you get any stars using this technique?
I have done observing of stars in infrared at nighttime. I haven't tried it during the day, but the sun is an enormous source of infrared, which would make it challenging to see stars during the day, but it's a good thing to try. This is a stack of, it's a mosaic of 3 frames, and each frame is a stack of the top 10% of about 1,000 frames. Next, please. So this is a more recent image collected at the 10th annual Video Star Party in Johnstown last weekend. The transparency was terrible the whole weekend, but the seeing was fabulous. I've never recorded such high quality images of the sun before, and Simon was there and he will attest to it that it was amazing. So again, outer images are from the 98 millimeter refractor with the Beta Herschel wedge. Calcium K filter, lots of detail in these spots. And then the IR high pass. And then this was the view through the little 35 millimeter Lund solar scope. So I found it interesting to compare each of these photos. And I was actually surprised when I laid them side by side that this very bright region here, which we identified to be an M1.5 flare, I think was it that Michael said, that we watched evolve during the day of our observing, which was very exciting, is not actually associated with the sunspot. The sunspot's over here. This flare is coming up kind of in this empty space here, which is kind of weird. Like looking at these 2 images, you would never know that there was a major flare erupting from the surface. But it's all, we're looking at it in 3D. So this is a layer above what we see here and here. So the gases at different depths are doing different things. It's kind of fascinating to see and to compare the 3. Next, please.
And Jim, they were taken roughly at the same period of time, or?
They were all taken within about a half an hour, a period of a half an hour. This was taken the following day, so I believe this was on Saturday. And this is the best image I've ever been able to achieve on the sun. So this is just visual band, UV IR cut filter on the Herschel safety wedge. And this is a 4 times Barlow on my 98 millimeter, so about f24. Wow. And yeah, the granulation and the sunspot details are, I was just floored. Even the live view on the screen was impressive to see. So I'm very happy with that. So that was what we did during the day. And at night, next please, we did our best to observe deep sky at night. Most of the time we could only look straight up, because around the horizon it was very hazy, but straight up, luckily it was the summer triangle. So this is actually a single frame, 60 seconds exposure from a universe that's been paired up to a 135 millimeter lens, no filters. And what we're looking at is, right here is M11, the wild duck cluster. This dark area up here is Barnard 111, dark nebula, and then this is Barnard 119, another dark nebula. So this is at the feet of Aquila, the eagle. And this bright patch here is the Scutum star cloud, which is basically a window through all of the nearby dust and gas to the center of our galaxy, where the actual center is kind of down here in Sagittarius. So this is just north of Sagittarius, and it's a window into the core of our galaxy, which I thought was pretty cool. Next, please. One of my favorite nebulous regions in Cygnus is the Gamma Cygni Nebula, which this is Gamma Cygni here, which is the center of the cross. I call it the Dragon Nebula, because I think that if this is an eye, and this open cluster is an eye, and this is the mouth here, 2 big flaring nostrils, that to me it looks like a Asian dragon, like here's the back. So I call it the Dragon Nebula. Feel free to use that name. So this is the Universe camera again, a single 2-minute frame. Yeah, I was pretty happy with that. I was using the camera just for observing. I wasn't collecting a series of lights to do processing after. I actually had my Extreme and the Universe side by side on the screen, comparing same exposure, what I could get. I was pretty happy with it. And the last one is the North American Nebula. This is Deneb over here. The field of view here is about 10 degrees. So I was quite wide field of view. You can see the North American Nebula there, the Pelican, as well as some outlying nebulosity and the larger dust cloud that kind of encapsulates this whole area. And even some dark regions up here. So I thought that was a good shot too. Again, 2 minutes, single frame exposure. That's it. Thank you.
Perfect. Yeah, let's do that. So we're going to squeeze in a couple of images from the Smart Scope, and we're just going to share those really quickly here. You want to come back up?
Hi again. You thought you got rid of me, eh? I tried to get Jim to do this, but yeah, I'll get you, Jim. All right. Just to give you a really brief update, we continue to work on the Smart Scope. Things are coming along quite nicely there, and last week, Jim and I were out testing a DSLR on the Smart Scope there, and just to get a feel for how things are working there, and we made some good progress there. So these are just some simple test shots that I thought I'd show you, and just to let you know that Smart Scope, yes, is still alive, and coming to a theater soon near you. So just some test shots, all 30-second exposures. Some of them are stacked. This is M13 in Hercules there, globular cluster there, and that turned out not too badly there. We had a nice fortunate little window of clarity there that allowed us to ping off some of these images. Next one, please. This one again, this is all at prime focus with the Smart Scope there. Also note that the Smart Scope itself hasn't been collimated. There's a lot of stuff that we still need to do with it there, but I was very encouraged when we started getting down some of these results, especially since these are unguided exposures. And again, because of various reasons, we were limited to 30-second long subframes there. So M57, the Ring Nebula with the central star very clearly visible. And then the last one I have to show you there, did a piece on the moon there as well. So we've been experimenting with different cameras there and different targets there, quite a close-up on the moon there. This was actually taken with the moon only about 3 or 4 degrees above the horizon. So even with, through a very murky, turbulent atmosphere, we managed to get some half-decent details there. So stay tuned. We'll let you know. We've got a few bits and pieces on order that will finalize our mechanical configuration of the Smart Scope itself, and then we'll hope to try to get the online operation, the actual remote operation, going as a sort of the last thing that we need to do, though. So we are working on it. Take care. Thanks.
Thanks again, Paul. You're right, Paul. We're probably due for an update on the Smart Scope.
You hear that, Jim?
Yeah, Jim Maxwell. Yeah, on our Ottawa Center's remote-controlled observatory and scope. Okay, we're
About the tickets.
sure.
On sale starting this month.
Why don't you come back up, Gary?
I just want to mention, Gord mentioned that the dinner tickets will be $42, same price as the last two years. They will be on sale starting next month. Sylvie Letourneau graciously always makes them for us. So they'll be sale next month for sure. So we have September, October, November. We take cash, the funny money. Also check made out to the Ottawa Centre RASC. And that's it. Thank you.
Thanks, Gary, for the reminder. Okay, so typically we have our meetings that we stream live on the internet. Tonight we did not, but however, we will. This meeting is being recorded by Ennis, and will be posted on the internet. We'll send out the coordinates of where you can find it on the internet, and I imagine in the coming days when it's posted. Next. So Estelle's Book of the Month. Well, you probably recognize this. Dan Falk was here a couple of months ago. He's a journalist and science author. This is his pick. I know a number of you. I think there was actually 24 or 28 books that Dan signed here. He was quite grateful for that event. Next, please. Okay, you're welcome to join us for drinks and some review of the night, if you will, and talk anything, all things astronomy at Kelsey's up the street. We head over there right after this. Next. Tonight there was 99. Gary, did you count me? Well, surely we could have hit 100. Okay, didn't count me. Well, or maybe. Thanks everyone. Thanks, Peter. All the best to you. Okay, and your school, Bianca. I very much appreciate you taking your time again. And to all of the presenters and people sharing their images. Great selection tonight. Next. The next meeting is September 5th. So as you know, we skipped this typically the first Friday of the month. This time we skipped the Fridays because last Friday was civic holidays, so we don't like running on the holidays. Next, or the weekends of the holidays. For the in the next meeting, the people we have lined up here are Chuck to talk about what Chuck talks about, impact craters, and he's always interesting. And Carmen, really looking forward to this talk, is going to talk about historical figures in astronomy and the people who helped shape astronomy. So I'm delighted to have you back, Carmen, and one of your riveting talks. I think that's about it. Okay, so yeah, that's right. Okay, so that closes the meeting. Thanks, everyone. And again, if you're going to if you're able to volunteer for the solar event at CARP, please let me know. We're going to do the door prizes right now.